Hey there, and welcome to Somnifly. Where are we heading off to this time? Let me know in the comments below. Today, we're diving into the fascinating world of the interstellar medium and galaxies. We'll explore the cosmic clouds of gas and dust that fuel star formation and unravel the mysteries of countless galaxies scattered across the universe. So buckle up, hit that subscribe button, and turn on notifications. You won't want to miss a thing. Let's explore the universe together. Imagine drifting through space far beyond Earth's atmosphere. The silence is absolute, the darkness overwhelming. You look around, and apart from the distant pinpricks of stars, it seems like there's nothing, just an endless void. But that's an illusion. Space is not empty. It's filled with an invisible yet essential substance, the interstellar medium. This vast, diffuse material made of gas, dust, cosmic rays, and magnetic fields is the backbone of galaxies. It stretches between stars, weaving them into a single interconnected system. Without it, galaxies as we know them wouldn't exist. It's the raw material for star formation, the medium through which light from distant objects travels, and a key player in galactic evolution. But why does this matter? Because, in a very real sense, the interstellar medium is where stars are born and where they die. Every star you see in the night sky, including our sun, began as a dense knot of interstellar gas and dust, collapsing under its own gravity until nuclear fusion ignited at its core. And when a massive star reaches the end of its life, it doesn't simply vanish. It explodes as a supernova, scattering its enriched elements back into space. These elements mix with the interstellar medium, seeding the birth of new stars and planets. This cosmic cycle has been running for billions of years. The atoms in your body, the oxygen you breathe, the carbon in your cells, the iron in your blood, were forged inside ancient stars and spread through the interstellar medium before becoming part of Earth. In a very literal sense, we are made of stardust. Understanding the interstellar medium is crucial to understanding the universe itself. It shapes galaxies, determines the pace of star formation, and even affects how we observe the cosmos. Every beam of light from a distant star or galaxy must pass through this medium before reaching our telescopes. Along the way, it is absorbed, scattered, or re-emitted, altering what we see. Without knowing how the interstellar medium works, we could misinterpret fundamental aspects of the universe, like the distances to galaxies or the true nature of cosmic objects. But there's more. The interstellar medium doesn't just passively exist, it evolves. It's constantly stirred by exploding stars, shaped by powerful magnetic fields, and molded by the gravity of massive cosmic structures. It's a dynamic, ever-changing environment where new elements are forged and the building blocks of planets and life itself take shape. Studying the interstellar medium is like reading the biography of a galaxy. It tells us about its past, its present state, and even hints at its future. By analyzing the composition and movement of interstellar gas, we can trace the history of stellar explosions, detect hidden star-forming regions, and understand how galaxies grow and change over time. This lecture will take us through the hidden world of the interstellar medium and the evolution of galaxies. We'll explore its composition, the different phases of interstellar gas, the role of cosmic dust, and how these elements shape the grand structure of the cosmos. Along the way, we'll uncover the incredible mechanisms that drive galaxy formation, the turbulent interactions of gas clouds, and the mysterious influence of supermassive black holes at their centers. Everything in the universe is connected, from the smallest dust grain floating in space to the most massive galaxies stretching across billions of light years. And it all begins with the interstellar medium, the unseen fabric that weaves the cosmos together. So let's begin. What exactly is the interstellar medium made of? If you could scoop up a handful of the interstellar medium, what would you find? At first glance, it might seem like a near-perfect vacuum, almost nothing at all. But if you look closer, much, much closer, you'd see that this vast emptiness is actually filled with billions upon billions of individual atoms and molecules, drifting through space like an incredibly thin cosmic fog. The primary ingredient in this mix is hydrogen, the most abundant element in the universe. It makes up roughly 96% of the interstellar gas. The second most common element is helium, which accounts for nearly all of the remaining 4%. But then There's something even more interesting: a tiny fraction of heavier elements like carbon, oxygen, nitrogen, iron, and silicon. These elements, although making up less than 1% of the interstellar medium, are the building blocks of planets, moons, and even life itself. Now, interstellar gas isn't just floating around as individual atoms. It can exist in different forms: neutral, ionized, or even molecular, depending on its environment. In the colder regions of space, hydrogen atoms pair up to form molecular hydrogen, the key ingredient in the birth of new stars. In hotter areas, the gas is ionized, meaning electrons are stripped away from their atoms by intense radiation from nearby stars. But gas isn't the only thing drifting through space. There's also cosmic dust, tiny solid particles that, despite their name, are nothing like the dust you find on a bookshelf. These grains are microscopic, often smaller than a speck of smoke, yet they play a crucial role in shaping the galaxy. They're made of carbon compounds, silicates, frozen water, and even complex organic molecules. Cosmic dust absorbs and scatters light, changing the way we see distant stars and galaxies. It also provides surfaces where chemical reactions take place, leading to the formation of complex molecules that might be the precursors of life. And then there are cosmic rays, high-energy particles that zip through the galaxy at nearly the speed of light. These aren't ordinary gas particles. They're charged nuclei that have been accelerated by exploding stars and powerful magnetic fields. When they collide with atoms in the interstellar medium, they trigger reactions that can create rare and exotic elements. Now, here's something fascinating. Even though gas outweighs dust by about 100 to 1 in terms of mass, dust has an outsized influence on how galaxies evolve. It affects the chemistry of space, blocks harmful ultraviolet radiation, and even plays a role in cooling down gas clouds so that they can collapse and form new stars. All of these components, gas, dust, and cosmic rays, are woven together by magnetic fields, which crisscross the galaxy like invisible threads. These fields help guide the motion of charged particles, shape interstellar clouds, and influence how stars and planetary systems take form. So, the interstellar medium is far more than just empty space. It's a rich, complex mixture of matter and energy, constantly shifting and evolving. And within this vast cosmic soup, stars and planets are born, elements are forged, and the galaxy itself takes shape. But this material doesn't just sit around in a uniform cloud. It exists in distinct phases, with dramatic differences in temperature and density. So let's take a closer look. What are the different states of interstellar gas, and how do they shape the galaxy? Not all interstellar gas is the same. In fact, it exists in dramatically different states, ranging from freezing cold to scorching hot, from dense star-forming clouds to vast, near-empty voids. These different forms of gas, known as the phases of the interstellar medium, are shaped by energy from stars, supernovae, and cosmic radiation. Understanding these phases is key to understanding how galaxies evolve, how stars are born, and how matter circulates through space. Let's start with the coldest phase, where star formation begins. Imagine a vast, dark cloud drifting through space, made of hydrogen molecules, dust, and trace amounts of heavier elements. This is the cold, neutral medium, where temperatures drop to just 100 degrees above absolute zero. The density here is relatively high, though still much thinner than the best vacuum on Earth, which allows gravity to take hold. When parts of the cloud become dense enough, they begin to collapse under their own weight, forming the seeds of new stars. These cold clouds, often called molecular clouds, are the nurseries of the universe, where the next generation of stars and planets begins to take shape. But not all interstellar gas is this cold. Move into another region and you'll find a warmer, more diffuse gas spread throughout the galaxy. This is the warm neutral medium, where temperatures rise to about 10,000 degrees Fahrenheit. Here, hydrogen atoms float freely instead of clumping together into molecules. This gas isn't dense enough to form stars on its own, but it plays a crucial role in feeding the cold clouds and keeping the galactic ecosystem balanced. Now let's turn up the heat. Near young, massive stars, the gas becomes so hot that it loses electrons, creating what's known as the warm ionized medium. This gas is heated by intense ultraviolet radiation from stars, making it glow in beautiful, colorful nebulae. If you've ever seen images of the Orion Nebula or the Eagle Nebula, you've seen this ionized gas in action. These glowing regions are important because they mark places where new stars are forming, shaping their surroundings with powerful stellar winds. But what happens when stars die? When a massive star reaches the end of its life, it explodes as a supernova, releasing a shockwave of energy that blasts through the surrounding gas, heating it to incredible temperatures. This creates the hot ionized medium, where temperatures soar to a staggering millions of degrees Fahrenheit. This gas is so hot that it doesn't stay confined to the galaxy's disk. It expands outward, creating bubbles and superheated cavities that stretch across thousands of light years. These different phases don't exist in isolation. They constantly interact, shaping and reshaping the galaxy. Cold clouds collapse to form stars. Stars heat and ionize the surrounding gas. Supernovae blast hot gas into space, which then cools and becomes part of the cold medium once again. It's a never-ending cycle, an intricate balance of heating and cooling, compression and expansion. But there's another layer to this picture, where these different phases are located in the galaxy. The densest molecular clouds are found in the spiral arms, concentrated where stars are actively forming. The warm and ionized gas is spread more evenly throughout the galaxy, acting as a transition between the colder and hotter regions. And the superheated gas from supernovae, it extends far beyond the galactic plane, forming vast halos of hot plasma that envelop the entire galaxy. The interstellar medium, then, is not just one thing. It's a dynamic, ever-changing environment where different phases coexist and influence each other. These phases determine where stars form, how galaxies evolve, and even how we see the universe, as interstellar gas and dust affect the light traveling through space. But there's one more key ingredient that plays an essential role in all of this: interstellar dust. It's tiny, nearly invisible, but it changes everything. So what exactly is this cosmic dust, and why is it so important? If you could hold a tiny speck of interstellar dust in your hand, it would be smaller than a grain of sand, microscopic, nearly invisible. And yet these tiny particles shape the entire universe in ways we are only beginning to understand. They dim the light of distant stars, color the glow of nebulae, and even serve as the chemical laboratories where complex molecules form. But what is cosmic dust made of? It's not like the dust in your room, which is mostly dead skin cells and fibers. Interstellar dust is something far more exotic. It consists of silicates, carbon compounds, and frozen molecules like water, ammonia, and methane. These tiny grains, often less than a micrometer across, are scattered throughout the interstellar medium, drifting through space like smoke from an unseen fire. One of the most important effects of interstellar dust is that it changes the way we see the universe. Imagine looking through a foggy window. Everything appears dimmer and redder than it actually is. This is because dust absorbs and scatters light, with shorter blue wavelengths being scattered more than longer red wavelengths. The result? A phenomenon called interstellar reddening, where distant stars appear redder than they truly are. It's the same reason sunsets on Earth look red. The atmosphere scatters blue light more effectively, leaving only the longer red wavelengths to reach our eyes. But dust doesn't just block light, it re-emits it in the infrared. When ultraviolet and visible light from stars hits a dust grain, the grain absorbs the energy, heats up slightly, and then releases that energy as longer wavelength infrared radiation. This means that some of the most breathtaking images of space, like those taken by the James Webb Space Telescope, show us the glow of interstellar dust itself. By studying this infrared glow, astronomers can map out hidden structures of the universe, revealing cold star-forming regions, dusty galactic centers, and even planets forming around distant stars. Now, dust does something even more fascinating. It acts as a chemical reactor. In the coldest, darkest parts of space, atoms and molecules stick to the surface of dust grains, where they can interact and form new, more complex compounds. And this is where some of the earliest organic molecules in the universe may have formed, compounds that billions of years later would become the building blocks of life on Earth. There's also a strange and unexpected effect of interstellar dust. It polarizes light. When dust grains align with a galaxy's magnetic field, they preferentially absorb light waves, oscillating in certain directions. This creates polarized light, which astronomers can use to map out magnetic fields on a galactic scale. It's one of the few ways we can study these otherwise invisible forces, which play a crucial role in guiding the movement of interstellar gas and dust. Even though dust only makes up about 1% of the interstellar medium by mass, it has an outsized influence on everything from star formation to galactic evolution to the chemistry of space. It's not just cosmic debris, it's an essential part of the universe's life cycle, shaping the very fabric of galaxies. But light doesn't just interact with dust. It also encounters interstellar gas, which can absorb, scatter, and even shift its wavelength in complex ways. So how does interstellar matter affect the light we see from distant stars and galaxies? Let's explore the fascinating mechanisms of light absorption and scattering in space. Light is our only way of seeing the universe. Every star, every galaxy, every nebula, everything we know about the cosmos comes from the light that reaches us. But before that light can arrive at our telescopes, it has to travel through the interstellar medium, and that journey isn't always smooth. Along the way, it gets absorbed, scattered, and even altered, changing what we see and sometimes hiding entire regions of the sky from view. Let's start with absorption. What happens when light encounters interstellar gas or dust and gets swallowed up? The most dramatic effect of this is interstellar extinction, where distant stars appear fainter than they actually are. If you've ever driven through fog at night, you've seen something similar. Headlights look dimmer because water droplets absorb and scatter the light. In space, this effect is even stronger in regions dense with dust and gas, like the dark nebulae that blot out parts of the Milky Way. But absorption isn't uniform. Different materials absorb different wavelengths of light, which is why interstellar dust causes reddening. Short wavelength blue light is scattered away, while longer wavelength red light passes through more easily. This is why distant stars often look redder than they really are, and why astronomers have to correct for this effect when measuring a star's true color and temperature. Then there's scattering. What happens when light doesn't get absorbed, but instead changes direction? Think of sunlight hitting Earth's atmosphere. Blue light scatters more than red, making the sky appear blue. In space, the same thing happens. Dust grains scatter light in all directions, creating the hazy glow of reflection nebula, clouds of dust illuminated by nearby stars. But while dust mainly affects visible and infrared light, interstellar gas interacts with even higher energy radiation, like ultraviolet and X-rays. Hydrogen, the most abundant element in space, plays a key role here. When a hydrogen atom absorbs a high-energy photon, its electron jumps to a higher energy level. Later, when the electron drops back down, it re-emits light at a specific wavelength. This creates spectral absorption lines, dark bands in a star's light spectrum that tell us exactly what elements are present in the interstellar medium. In some cases, absorption is so extreme that certain wavelengths of light never make it through. The ultraviolet glow of young stars, for example, is almost completely blocked by interstellar hydrogen, which is why we need space telescopes to observe it. And in the case of X-rays, high-energy photons get absorbed by interstellar gas through a process called Compton scattering, where they lose energy by colliding with free electrons. And what about radio waves? Unlike visible or ultraviolet light, radio waves can pass through interstellar dust almost completely unimpeded. That's why radio telescopes can peer into the heart of our galaxy, seeing through dense clouds of dust that would otherwise obscure our view. However, even radio waves aren't entirely immune to the effects of interstellar matter. Free electrons scattered throughout space cause a phenomenon called dispersion, where lower frequency radio waves travel slightly slower than higher frequency ones. This effect is particularly noticeable in pulsars, rapidly spinning neutron stars that emit precise radio pulses. As their signals travel through the interstellar medium, different frequencies arrive at Earth at slightly different times, allowing astronomers to measure the density of free electrons in space. So, light never travels through space untouched. It's absorbed, scattered, reddened, and sometimes even completely blocked. But rather than being a nuisance, these effects give us crucial information about the interstellar medium. By studying how light interacts with gas and dust, we can map out hidden regions of space, determine the chemical composition of galaxies, and even measure the structure of the universe itself. But interstellar matter doesn't just passively affect light, it's also constantly moving and evolving. So, how does all of this material circulate within a galaxy? Let's dive into the grand cosmic cycle of matter, the interstellar medium's never ending process of recycling and renewal. Nothing in the universe stays the same forever. Stars are born, shine for millions or even billions of years, and then die, returning their material to space. This constant recycling of matter is what keeps galaxies evolving. It's the reason new stars can form, the reason planets exist, and even the reason life is possible. The interstellar medium isn't just a passive environment where stars appear and disappear. It's an active, dynamic system where gas and dust are continuously processed, enriched, and redistributed. Let's start at the beginning, star formation. Imagine a cold, dense molecular cloud drifting in space. These clouds, vast collections of hydrogen gas mixed with cosmic dust, can be dozens or even hundreds of light years across. Over time, gravity starts pulling the gas together, creating denser and denser regions. If enough mass accumulates in one spot, the cloud collapses, heating up as it contracts. Eventually, deep within the heart of this collapsing cloud, the temperature rises high enough for nuclear fusion to ignite. And just like that, a new star is born. But stars don't live forever. When a star reaches the end of its life, it gives back everything it took from the interstellar medium and more. For stars like our sun, this process is relatively gentle. Over billions of years, they slowly shed their outer layers into space, forming beautiful glowing shells called planetary nebulae. The remaining core cools and shrinks, becoming a white dwarf, a dead but still glowing ember of a star. For more massive stars, though, the end is much more violent. When a giant star runs out of fuel, its core collapses in a fraction of a second, triggering a supernova explosion. The explosion rips through space, blasting heavy elements, carbon, oxygen, iron, gold, even uranium, out into the interstellar medium. These explosions don't just create and scatter new elements. They also send out powerful shock waves that compress nearby gas clouds, triggering the birth of the next generation of stars. But supernovae aren't the only way the interstellar medium gets enriched. Even before a massive star explodes, it releases a steady flow of material through something called stellar winds. These winds, streams of charged particles moving at thousands of miles per second, carry away elements that the star has produced in its core. Over millions of years, these winds shape entire regions of space, carving out bubbles and cavities in the interstellar medium. Now, here's something fascinating. Not all of this gas stays in the galaxy. Some of it gets blown out into intergalactic space, forming enormous galactic fountains. Supernovae and stellar winds can push gas so far away that it escapes the galaxy's gravity entirely. But over time, some of this material cools down and falls back in, raining down onto the galaxy like cosmic precipitation. This process helps regulate star formation. If too much gas is lost, the galaxy will stop producing new stars, but if too much falls back in too quickly, it can trigger intense bursts of star formation. One of the biggest mysteries in astrophysics is just how efficient this process really is. You might think that most of the gas in a galaxy eventually turns into stars, but in reality, only a small fraction, less than 10%, ever becomes part of a star. The rest is constantly being stirred up by turbulence, pushed around by supernovae, and mixed by magnetic fields, preventing it from collapsing all at once. So, the interstellar medium isn't just a random collection of gas and dust. It's a living, breathing system that cycles matter through different phases, from diffuse clouds to dense star-forming regions, from the fiery deaths of stars to the creation of new ones. And throughout all of this, an invisible force is at work, shaping how gas moves, how stars form, and even how entire galaxies evolve. That force? Magnetic fields. But how do we even know that magnetic fields exist in space, and how do they influence the interstellar medium? Let's take a closer look at one of the most mysterious and powerful forces in the universe. If you could see magnetic fields in space, you'd notice that they are everywhere, woven through galaxies like invisible threads stretching across light years, guiding the movement of gas, dust, and even cosmic rays. These fields might be invisible to the eye, but their effects are undeniable. They shape how interstellar clouds collapse to form stars, influence how cosmic particles move through space, and even affect the overall structure of galaxies. But how do we know they exist? After all, we can't just fly out into space and hold up a magnetometer. Instead, we detect them through their effects on light, charged particles, and even entire gas clouds. One of the first clues came from an unexpected source: starlight. In the 1940s, astronomers noticed something strange. The light from distant stars wasn't just dimmed by interstellar dust, it was also polarized. This meant that the light waves were being forced to vibrate in a specific direction. The cause? Tiny dust grains aligning themselves along magnetic fields, much like iron filings around a bar magnet. By studying the way light is polarized, scientists could start mapping out the structure of these invisible cosmic forces. But that's just one method. Another comes from Zeeman splitting, a phenomenon where strong magnetic fields slightly change the energy levels of atoms, subtly shifting the wavelengths of light they emit. By analyzing these shifts, astronomers can measure the strength and direction of interstellar magnetic fields, even in distant galaxies. And then there's synchrotron radiation. When cosmic rays, high-energy charged particles, move through a magnetic field, they spiral around the field lines at nearly the speed of light, giving off faint but detectable radio waves. By studying this radiation, scientists can trace the twisted, tangled structure of galactic magnetic fields, revealing how they interact with interstellar gas. But what do these fields actually do? For one, they influence how gas flows through the galaxy. Without magnetic fields, interstellar gas would behave like a simple fluid, moving according to gravity and pressure. But in reality, these fields create an invisible scaffolding that resists compression, slows down the collapse of gas clouds, and even channels the movement of material across light years. This means that magnetic fields directly affect where and how stars form. They also control the motion of cosmic rays, the high-energy particles produced by supernovae and other violent cosmic events. If there were no magnetic fields, cosmic rays would shoot off in random directions. But because space is threaded with these invisible forces, cosmic rays follow twisted, looping paths, bouncing through the galaxy like subatomic pinballs. This motion isn't just random. It plays a crucial role in heating the interstellar medium and even in triggering the formation of new stars. But the role of magnetic fields doesn't stop at individual clouds or cosmic rays. They shape entire galaxies. In spiral galaxies like the Milky Way, magnetic fields follow the spiral arms, reinforcing the structures we see. In galaxies undergoing violent collisions or rapid star formation, magnetic fields can be twisted and stretched, influencing how gas is distributed and how fast stars form. And here's something even more astonishing. Magnetic fields might have played a role in the very formation of galaxies themselves. In the early universe, before stars and galaxies existed, tiny magnetic fields may have influenced the movement of primordial gas, helping to seed the structures we see today. Even now, we see evidence that magnetic fields exist on cosmic scales, stretching across vast filaments of gas connecting entire clusters of galaxies. So while they might be invisible, magnetic fields are one of the most powerful yet least understood forces in the universe. They shape the interstellar medium, influence the birth of stars, guide the movement of cosmic rays, and even sculpt the large-scale structure of galaxies. And speaking of galaxies, let's zoom out from the interstellar medium and take a broader look at these vast cosmic cities of stars, gas, and dark matter. How do we classify galaxies, and what can their shapes tell us about their history and evolution? When you look up at the night sky, the stars seem scattered randomly, like distant points of light with no particular pattern. But if you step back and view the universe on a larger scale, a striking order emerges. Stars are not isolated. They are grouped into vast cosmic structures called galaxies, each containing billions or even trillions of stars, along with gas, dust, and dark matter. Galaxies come in different shapes and sizes, and astronomers have long sought to classify them. One of the first and most famous classification systems was developed by Edwin Hubble in the early 20th century. He grouped galaxies into three main types: spiral, elliptical, and irregular. Let's start with spiral galaxies, the most recognizable and arguably the most beautiful. These galaxies have a flat, disc-like structure with sweeping spiral arms that extend outward from a central bulge. The Milky Way, our home galaxy, is a classic example of this type. The spiral arms are not just decorative. They are dense regions of gas and dust where new stars are actively forming. This is why spiral galaxies tend to have many young, bright stars scattered throughout their arms. But not all spirals are the same. Some have a clear, round bulge in the center, while others have a bar-shaped structure cutting through the middle. These are called barred spiral galaxies. The bar acts like a conveyor belt, funneling gas from the outer regions into the center, which can trigger bursts of star formation or even feed the supermassive black hole lurking at the core. Then there are elliptical galaxies, which look completely different. Instead of structured spiral arms, they appear as smooth, featureless ellipses, ranging from nearly spherical to long, stretched-out ovals. These galaxies tend to be older and contain very little gas and dust, which means they have stopped forming new stars. Instead, they are dominated by ancient reddish stars, remnants of a much earlier era in galactic history. Some of the largest galaxies in the universe are giant ellipticals found at the centers of galaxy clusters where they have grown by absorbing smaller galaxies over billions of years. And then we have the irregular galaxies, the cosmic misfits. These galaxies have no defined shape and often look chaotic, as if they were torn apart or distorted. Many irregular galaxies were once spirals or ellipticals, but were disrupted by gravitational interactions, either from a collision with another galaxy or from the pull of a nearby massive object. Despite their chaotic appearance, these galaxies are rich in gas and often have intense regions of star formation, making them some of the most dynamic and rapidly evolving galaxies in the universe. Galaxies don't exist in isolation. They interact, collide, and even merge, changing their shapes over time. A spiral galaxy can become an elliptical one if it undergoes a major merger, absorbing its spiral structure into a more amorphous shape. Smaller galaxies can be stretched and torn apart by the gravity of larger ones, leaving behind long trails of stars and gas. These interactions are a key part of galactic evolution, and they give us clues about how galaxies have changed over billions of years. So while galaxies might seem like static structures, they are actually constantly evolving, shaped by their internal dynamics and their interactions with their cosmic neighbors. Their shapes tell a story, a history of star formation, mergers, and transformations. But how did these galaxies form in the first place? What forces shaped them in the early universe, and how have they grown over time? To answer that, we need to travel back billions of years to the birth of the first galaxies. If we could rewind the universe back to its earliest moments, we'd see a very different cosmos, one without galaxies, without stars, without even complex atoms. Instead, the universe was filled with a nearly uniform sea of hot hydrogen and helium, created in the first few minutes after the Big Bang. But over billions of years, that smooth soup of gas somehow clumped together, formed structures, and eventually gave rise to the galaxies we see today. So how did this happen? It all began with tiny quantum fluctuations, microscopic differences in the density of the early universe. These fluctuations, stretched by cosmic expansion, became the seeds of galaxies. Over time, gravity amplified these small variations, pulling gas together into denser regions. These regions grew into dark matter halos, huge, invisible scaffolds that provided the gravitational pull needed to collect ordinary gas and form the first galaxies. But galaxies didn't form all at once. The first structures were small, irregular clumps of stars and gas, much smaller than the massive spirals and ellipticals we see today. These early galaxies grew by merging with each other, colliding, combining, and reshaping themselves over billions of years. This process, known as hierarchical assembly, explains why we see such a wide variety of galaxy shapes and sizes. One of the key drivers of galaxy growth was cold gas accretion. As intergalactic gas fell into a galaxy's gravitational grip, it didn't just drop straight in, it formed rotating disks, which later developed into the spiral structures we see in galaxies like the Milky Way. This cold gas provided the raw material for intense bursts of star formation, lighting up the universe with new generations of stars. But galaxy evolution wasn't always smooth. Massive collisions, some of the most violent events in the cosmos, shaped galaxies in dramatic ways. When two galaxies of similar size collided, their spiral arms were often destroyed, and they merged into a single, more massive elliptical galaxy. This explains why many of the largest galaxies we see today are ellipticals. They are the end products of countless galactic mergers. And mergers weren't the only force at work. Supermassive black holes, millions or even billions of times the mass of the sun, formed in the centers of early galaxies, feeding on gas and unleashing enormous amounts of energy. When these black holes consumed too much material too quickly, they became quasars, blasting out radiation that could push gas away and shut down star formation. This process, called feedback, helped regulate how galaxies grew, preventing them from forming too many stars too quickly. Even today, galaxies continue to evolve. Some are still growing by absorbing smaller galaxies. The Milky Way itself is in the process of merging with several dwarf galaxies right now. Others have run out of gas and stopped forming new stars, slowly fading into the background of the cosmos. So galaxies aren't static. They are living, changing systems, shaped by mergers, gas flows, and the influence of supermassive black holes. Their evolution is driven by an intricate balance of forces, from the pull of gravity to the explosive power of quasars. And speaking of black holes, their role in galaxy evolution is even bigger than we once thought. Every large galaxy seems to have a supermassive black hole at its center. But what exactly do these cosmic giants do, and how do they shape the fate of their host galaxies? At the heart of nearly every large galaxy lies a supermassive black hole, a gravitational monster millions or even billions of times the mass of the sun. These cosmic giants are more than just exotic objects lurking in galactic centers. They play a fundamental role in shaping the evolution of galaxies themselves. From triggering powerful jets of energy to regulating star formation, they are some of the most influential forces in the universe. But how do we even know these black holes exist? After all, black holes emit no light, and we can't see them directly. The answer lies in their gravitational effects. In the center of our own Milky Way, stars are orbiting an invisible point with incredible speeds, moving as if they are being pulled by something immensely heavy, yet completely dark. The only explanation? A supermassive black hole, Sagittarius A, with a mass of about 4 million suns. And the Milky Way's black hole is relatively quiet. In some galaxies, the central black hole is actively consuming gas, and when that happens, the effects are dramatic. As matter spirals toward the black hole, it heats up to extreme temperatures, releasing enormous amounts of energy in the form of radiation, high-speed winds, and even jets of charged particles moving at nearly the speed of light. These blazing centers of activity are called active galactic nuclei, or AGN. When an AGN is particularly bright, we call it a quasar. And in the early universe, quasars were among the most brilliant objects in existence, outshining entire galaxies. But here's the surprising part. These supermassive black holes don't just passively consume gas. They can influence the entire galaxy around them. The powerful radiation and winds from an active black hole can blow away interstellar gas, shutting down star formation and preventing new stars from forming. This process, known as feedback, helps explain why some massive galaxies suddenly stop producing stars and become red and dead ellipticals. And yet, in some cases, these black holes can also trigger star formation. When jets from an AGN blast through the interstellar medium, they can compress gas clouds, causing them to collapse and form new stars. So rather than simply destroying galaxies, supermassive black holes are part of a delicate balance, sometimes shutting down star formation, sometimes encouraging it, and always playing a role in the life cycle of galaxies. But where did these black holes come from in the first place? That's still one of the biggest mysteries in astrophysics. Did they start as smaller black holes that merged over time? Or did they form from massive gas clouds collapsing directly in the early universe? Even now, we don't fully know. What we do know is that they've been growing alongside their galaxies for billions of years, influencing their shape, structure, and future. And galaxies don't exist alone. They are part of vast structures. clusters of galaxies bound together by gravity, stretching across millions of light years. These clusters are connected by enormous filaments of gas and dark matter, forming what we call the cosmic web, the large-scale structure of the universe itself. So, how do galaxies interact on these enormous scales? What happens when entire galaxy clusters collide, and what can these vast structures tell us about the hidden forces shaping the cosmos? Galaxies are not isolated islands in space. They exist in massive clusters, bound together by gravity, stretching across millions of light years. These clusters are the largest gravitationally bound structures in the universe, containing hundreds or even thousands of galaxies, vast amounts of hot intergalactic gas, and an invisible but dominant presence: dark matter. Understanding these colossal structures helps us piece together the story of how galaxies evolve, how dark matter shapes the cosmos, and even how the universe itself is expanding. One of the defining features of galaxy clusters is their hot gas, which is so energetic that it emits X-rays instead of visible light. If you could see in X-ray vision, these clusters wouldn't just be collections of galaxies. They'd be glowing clouds of plasma, heated to tens of millions of degrees by the combined gravity of the cluster. This hot gas makes up a significant portion of a cluster's total mass, but even it is overshadowed by dark matter, the mysterious substance that provides the majority of the cluster's gravitational pull. And these clusters don't just sit still. They interact, collide, and even merge with one another in some of the most dramatic events in the cosmos. When two massive clusters collide, the shock waves ripple through the intergalactic gas, heating it up even more and creating some of the most energetic events in the universe. One of the best examples of this is the Bullet Cluster, where astronomers have been able to see dark matter's effects directly. As two clusters smashed together, the hot gas from each slowed down due to friction, but the dark matter passed through unimpeded, revealing itself through gravitational lensing, the way it bends light from background galaxies. Speaking of gravitational lensing, this effect is one of the most powerful tools astronomers have for studying galaxy clusters. Since gravity bends light, massive galaxy clusters act like cosmic magnifying glasses, distorting and amplifying the light from more distant galaxies behind them. This allows us to see some of the farthest and faintest galaxies in the universe, giving us a window into the early cosmos. But galaxy clusters are not the largest structures in existence. They are part of an even greater cosmic web, a vast interconnected network of galaxies, filaments of gas, and dark matter stretching across the universe. Between these filaments are enormous voids, regions nearly empty of galaxies, spanning hundreds of millions of light years. This large-scale structure of the universe was shaped by tiny density fluctuations in the early universe, the same ones that led to the formation of galaxies themselves. So galaxy clusters are not just collections of stars and gas. They are key players in the structure and evolution of the universe itself. They show us the effects of dark matter, the role of high-energy physics in shaping galaxies, and the way gravity sculpts the cosmos on the grandest scales. But our journey doesn't stop here. The study of the interstellar medium, galaxy evolution, and cosmic structures is far from over. As technology advances, we are uncovering new mysteries about the universe every day. So what does the future hold for this field of astronomy? And what are the biggest questions still waiting to be answered? The more we study the universe, the more we realize how much we still don't know. The interstellar medium, galaxy evolution, and the large-scale structure of the cosmos have given us incredible insights into how the universe works. But at the same time, they have raised even bigger questions. What role do magnetic fields truly play in star formation? How exactly did the first supermassive black holes form? What is dark matter, and how does it shape the evolution of galaxies? These mysteries drive modern astrophysics, pushing us toward new discoveries. One of the most exciting frontiers in this field is the next generation of telescopes and space missions. The James Webb Space Telescope has already begun revealing never-before-seen details of interstellar clouds, distant galaxies, and even exoplanet atmospheres. Meanwhile, powerful new observatories like the Vera C. Rubin Observatory and the Square Kilometer Array will allow us to map the distribution of dark matter, trace the evolution of galaxies across cosmic time, and even detect the faint radio signals from the very first stars that ever formed. But it's not just observations that are advancing our understanding. Supercomputer simulations are becoming powerful enough to recreate the birth of galaxies, the motion of interstellar gas, and the formation of cosmic structures over billions of years. These models help us test theories that can't be directly observed, allowing us to explore the universe in ways that were once impossible. At the same time, new questions are emerging. What is the true nature of dark energy, the mysterious force causing the universe to expand faster and faster? Could there be unknown physics at play in galaxy formation that we haven't yet discovered? The more we learn, the more the boundaries of our understanding are pushed outward. The study of the interstellar medium and galaxy evolution is not just about looking at distant objects. It's about understanding our place in the cosmos. Every atom in our bodies was once part of the interstellar medium, forged in the heart of ancient stars and scattered across space before becoming part of Earth. The same forces that shape galaxies have also shaped our own existence. And so, as we continue to peer deeper into the universe, we are not just looking outward, we are also looking back in time, unraveling the story of how everything we know came to be. The journey is far from over, and the discoveries of the next decades may completely change our understanding of the cosmos. The universe is waiting, and we are just beginning to uncover its secrets. And before we sign off, here's a fun fact. While this video was rendering, my laptop's fans were roaring like a spaceship blasting off into deep space. If you want to help fuel my next cosmic upgrade, check out the links below. Thanks for watching, and see you in 4K.